In this video, we'll finally be going to part 3 of the nephron, okay? So we're going to be talking specifically about the loop of Henle. This means that we already covered the glomerulus, the proximal convoluted tubule, and now we get here, the loop of Henle. This is, in my opinion, the most difficult part of the whole nephron, but still, I can make it quite simple for you guys. So let's get into it. First off, what we need to know, what's special about the loop of Henle is that it is in a different place compared to the other two segments. So, the rest of the nephron. So notice this. You see this line. I'm separating the top of the nephron from the loop of Henle. I'm doing this because the top of the nephron, so this whole segment, is in what you call the cortex of the kidney. And the loop of Henle is in the medulla. Okay, so let me show you real quick again the kidney structure. So here we have it. This is the kidney. The cortex is this outer part, and the medulla is all these little segments here. So what I'm trying to say is that for the nephron, the medulla is located within. The loop of Henle, this part, is located inside the medulla, whereas all the other parts are in the cortex. Okay, just bear this in mind. Okay, now let's get into it. So here we have the loop of Henle. So I'm trying to make this simple. So this green part here represents the proximal convoluted tube that came in. This itself, this is actually the loop of Henle. And then this part here is going to be the next segment called the distal convoluted tubule. And then this part here will be the collecting duct, okay? I included these just because you'll see something matters, why you need to be able to see these, okay? You'll see why. So let's get to the basics. By the way, here is a little key, okay? A little thing that's going to explain what the things mean I'm showing. So if you see any of these structures, that's water. If you see any of these, that means salt, so sodium or chlorine. And these represent kind of channels that transport ions, so channels that will transport sodium and chloride. And then this will be a water channel, so water can pass through this. So ions can pass through this one, water can pass through this one, okay? So now let's continue from the proximal convoluted tubule. So we know now here our blood was filtered by size, so small molecules came in here, they were good and bad. Then we wanted to remove some of the bad molecules, so we wanted to remove some of the good molecules because we wanted to put them back into our bloodstream. So that's what we did in the proximal convoluted tubule. The good things were removed and put back into our blood. So now we have some bad things left and some water and things like that. Okay? Because water can be good and bad. Because if our body has too much water, we want to get rid of it, right? But if we have too little water, we want to keep some of it. So water can be both good and bad depending on how full you are, like how thirsty you are. Okay? So now we have it here. Let me show you. So the proximal convoluted tube, we have some water, we have some ions, and we have some other stuff. But for the purpose of the loop of Henle, only really cares about ions and water. Okay? So here we have it. The water and the ions flow in this direction. Okay? And then they will flow down here, up here, to the right, and down. And then from here, they will go into the ureter and then to your bladder, okay, and then out of your body. Now, what do we call this part of the loop of Henle, this segment here? And what do we call this segment? So the one going down, okay, from the proximal convoluted tube is called the descending limb. So let me show you. The descending limb, because it's going down, it's descending. And then the other one, guess what? It's called the ascending limb because it's going upwards, okay? So know that those two have slightly different names. Now comes the important part. So the descending limb has these channels, okay, or these little pathways that ions cannot exit, but only water can exit, okay? So like I said here, these little channels or pathways are water permeable, so only water can leave from them, okay? And then the ascending limb has these little pathways, so I made them a different color because they're different. They are permeable to ions, but not to water, okay? So we'll see exactly what this means. Now, first of all, something you need to understand. is now we have this water and the salt coming into this descending limb, okay? And as it's coming in, we have this, okay? So it flows in just like this, okay? The outside of this loop of Henle is an environment, right? So we have some, they call it extracellular area because it's outside of this this loop of Henle. So it's just empty space and it's got some stuff in it, okay? You need to know that as you go down the loop of Henle, so as you go down this way, the environment outside the loop of Henle becomes very concentrated. It becomes more and more concentrated with ions. So let me show you what I mean. So at this level, and you can imagine, you need to imagine that, remember, this is 3D, so don't get stuck on this 2D image. There's stuff all around. So at this level, there's stuff all around, like here, all around, there's ions. And at this level, there's stuff all around, everywhere. So it's not just 2D, remember, it's 3D. So now here I put a 1 ion because at this level, the outside is not that much more concentrated. It's not that concentrated. So around this level, here, all around, it's very small concentration of ions. Now as we move down, deeper into the loop of Henle, it becomes slightly more concentrated. So now I put 2 here to represent that everything on this layer, all around, is slightly more concentrated with ions. Now let's move slightly more down. Now it's going to get even more concentrated. So everything on this level is even more concentrated with ions. And as we go deeper, it gets more and more, okay? So the lower we go, the more concentrated the area around the loop of Henle is. Now, what does this mean? We know what this means. And by the way, if you don't worry about why this is the case now, because I'm going to explain that very shortly. Just know that as you go down, it gets more concentrated for some reason that I'll explain soon. Now, what does this mean if it gets more concentrated? So if this environment outside is concentrated, and we know this channel is permeable to water, what do you think is going to happen? Water will leave, right? Because water wants to even out concentration. If it's very concentrated outside, well, some water would want to leave to balance out the concentration, okay? So this means the lower you go, more water will leave, because this is so concentrated that you need a lot of water to leave to even out the concentration, okay? So this is the concept of osmosis. So make sure you know what osmosis is. Osmosis is pretty much just water evening out concentrations. The more concentrated it is on the outside, the more water would want to leave to even it out, okay? Or make it less concentrated. So by that logic, as the stuff in the loop of Henle travels down here, some water will leave, and then more water will leave, and even more. So more and more water will leave the lower we go. So eventually, but no ions will leave. Very important. No ions will leave because these are not permeable to ions. Okay, only water can leave. So by the time we get here, we will still have some water because not all the water left. Just all the water left in order to the right amount of water left to make the outside, to try and even out the outside. Okay, so we'll still have some water left and all our ions because no ions were able to leave yet. Okay, so now we approach the ascending limb. Now this is where we're going to understand why this concentration gradient looks like this. Why there's not that much ions high and a lot of ions low. Okay, so let me show you. So now we have our solution keeps moving up. So we got some ions and we got some water. Okay, not that much water because a lot of it left already. Okay, during the descending limb, but we still have all our ions. Now these pumps or these channels can move out ions. Okay, so at this point we have so many ions at this point where I'm pointing now. And so when we get in here, these pumps have such a wide variety, such a large amount of ions to take and send out. So at this level, a lot of ions will be sent out through these pumps like this. They will be sent out either direction. Remember, I'm trying to emphasize the 3D point. So I put pumps on both sides to show that it's not sending it just one way. It's sending it out in every direction of this tube. Because remember, a tube is 3D. Okay, understand that. So these channels will send out ions. And since this level has so many ions to choose from, we will get a lot of ions being sent out. Let me show you. In fact, it's going to be this many. So many, okay? Now, as we move slightly higher, our ions are running out. So we're getting a slightly less ions, which means these pumps have slightly less ions to choose from, okay? So instead, they send slightly less out, but they still send a lot out. So it's going to be this much. And now we move higher, and now there's even less ions to choose from. So these ions only have a certain amount to choose from, so they send out even less, but they still send some out. So, do you see the pattern? Now we get higher and there's even less to choose from. We're actually running out now of ions completely. So, they send out 2. And then the final one sends out 1, or the least amount. Okay, do you see now? So, the ascending limb is the one that is creating this concentration gradient. So this concentration gradient that I told you I was going to explain before, I just explained. This concentration gradient is created by this thing. This ascending limb pumps the ions out in all directions, so the ions can diffuse and reach here and reach everywhere. And that's why the concentration gradient looks like this, okay? So what I made here applies exactly to here. All of these ions will diffuse so all of these ions here will diffuse in this layer and reach here, okay? So it's 3D, understand that. So that's why it happens. Now, you might ask me now, okay, that's great, but what's the purpose of all this? The purpose of all this is super, super important, because right now you may not see the purpose, but it's really important that we create this concentration gradient, okay? So I showed you now how it's created and what it does to water. So now we have some ions and water left. So not everything was sent out. We still have some left, okay? And they approach now the distal convoluted tubule. Now, after that, I'm not going to explain what's going on here. This will be in another video, but nothing important happens here for now regarding water and ions. So now we get to what we call the collecting duct. That's the final stage. So we have a whole bunch of water and salt, okay? We still have some water and salt left. Now, this is the stage that is going to determine how much water is going to be peed out and how much water is going to be kept inside our body. Okay, what do I mean by this? So, for example, say you are extremely dehydrated. Okay, you need to keep as much water in your body as possible. What's going to happen is this. Your body will be smart and it will create these pumps. Okay, these pumps can be removed and added whenever needed. So let's say right now you're really thirsty, you're really dehydrated, and your body needs to keep all the water inside and not let it pass out through your urine. Okay, so what it's going to do, it's going to synthesize this pump. This pump is permeable to water, just like this one, except this pump can be removed and added whenever wanted. So what happens when we add this pump here at this location? That means a little bit of water will be able to leave because it's not too concentrated outside. So we won't be able to keep too much water inside our body. What if I put the pump here? Or let's just say here. Now it's quite concentrated, so quite a lot of water will be removed and kept inside our body. What if I put it all the way down here? Then almost all the water we have here can be put back into our body and we'll pee almost nothing out. Okay, so do you see why this concentration gradient was made? It was made so that our body can handle how much water we keep or pee out, because water flows by diffusion. So the only way we can get water out of this collecting duct is by diffusion. So we can't pump it out using energy. It needs to diffuse out, and the only way we can make it diffuse out is by creating this concentration gradient that we can use to let certain amounts of water out, depending how much. Now, let's say you're extremely full of water. You want to pee out as much as possible. You're full. Then your body will just remove all these little pumps, okay? So it will just decide not to use them. And then no water will be able to pass. And so it will all be kept inside the nephron and be peed out. Okay, even though there's this high concentration gradient and water in reality really wants to leave, but it can't, so you'll pee it out. So you see, I hope this really made sense. It's quite complicated, I understand, but if you can get this concept, then that's great. One last thing. So all these water and ions all this water that we made leave here, and all the ions we sent out, they can also they also obviously can enter our bloodstream, right? Because sometimes we reabsorb this water, so we let the water out, or we let the water come out of here so that we can put it back in our bloodstream. So what I want to show is this. So remember, we have this efferent arteriole that goes next to the proximal tube, so some good things can be put back into it. So the same way that can happen, we can also have this artery continue and come next to our, just like this, come next to our loop of Henle, just like this, and pick up all those things that we send out, all the water we send out and all the ions we sent out. It can help pick it up and put it back into our bloodstream, okay? So just know that this arteries always follow our nephron, because our nephron will send stuff in and need to take stuff out of the bloodstream, okay? So I hope this made as much sense as possible.